Hey guys, welcome back to a new video. In this session, we'll be learning how to find the domain of any function. And we'll be doing so by solving a multitude of exercises step by step. And the timestamp for each exercise can be found in the description below. Now, as always, if you have any questions along the way, feel free to post them in the comments down below or join the community and visit our Discord server where you can freely interact with fellow students and myself. If you like the video, give it a thumbs up, and with that said, let's get into the video. But before we go to the exercises, we want to know what we're actually doing, and that's why I will take just a minute to explain what the domain of a function actually is. To do this, we consider the black box representation of any function. In this representation, we start from an x, which is an input number, and we plug it into this black box, which we call f. And then the output of this black box is another number y, which we can also write as f of x. So what this function basically does is transform an input number x all the way to an output number y. However, not any number x can be plugged into this box, which means that the function does not necessarily accept any number x. And this is where the domain of the function comes in. The domain of a function is the set of numbers for which it can output a valid number y. And to see how this works visually, let's consider the set of all real numbers as this black blob. And consider now that for this specific function, only the numbers from this green subset will return a valid output y. And this green subset is then called the domain of this specific function. In practice, this means if you pick any number from this subset, the function will accept it and it will transform it in a valid output y. However, if you take a number outside of this subset, then the function will not accept this number and therefore there will not be any output y. And then the goal of this video by doing exercises is to determine exactly what the green subset of R actually is for any specific function. And that is what we'll be doing right now by going to the first exercise. And the first function that we'll be looking at is the easiest function that we can think of, namely f of x is equal to x. This means that if you input any number x into our black box function, it will simply return the same number x again. And now to find the domain of this function, we always start with the question whether we can think of any x being a real number that might give this function some trouble. Or in other words, think if we can find any x for which this function simply cannot give a valid output. For instance, let's try a negative number, let's say -5. This means that f of -5, well, the function simply returns the input itself, will simply be -5. Alright, so let's take 0 for example. So f of 0, well, will simply be 0. And we quite quickly see that any number that we use as an input is simply the output. Therefore, we can conclude that there will not be any real number x for which this function cannot return a valid value, because the function will simply return x itself. So if x is a valid number, then the output will also be a valid number. This means that the domain will simply be the entire set of real numbers, R. Or we can write this differently as follows: from -infinity to +infinity in open brackets. This simply means all of the numbers between -infinity and +infinity. And the open brackets indicate that plus and -infinity are not really numbers. So they cannot be included in the set of real numbers. In the second exercise, we are going to look at the function f of x is equal to the cosine of x. And as you probably know, this is a periodic function, oscillating between the values -1 and +1. If you draw the graph of this function, for example, with on the x-axis x and on the y-axis y, which is the output of our function, then we will quickly see that this function just oscillates back and forth between +1 and -1, here being +1 and here being -1. And again, the exercise is to find the domain of this function, meaning to find the set of all numbers for which this function, in this case the cosine, returns a valid number. And if you fill in some values in the cosine of x, you quickly see that you can basically fill in any number and it will always return a number between -1 and 1. For example, if x is equal to 0, which is always a good value to check because this is a point where a lot of functions might not return a valid number, we simply see that the cosine of 0 is of course equal to +1, which is of course a valid output. If we fill in a negative number, for example minus pi, then we find that the cosine of minus pi is equal to 0. It is 0, but it's still a valid output, so a negative number seems to be working fine. And this of course you can do forever, and you will always find that you will get an output which is between +1 and -1. And as an aside, this of course is the range of the cosine of x, but the range of a function I will leave for another video. What's important here is that we can fill in any number we like and we will always get a valid result back. Therefore, the domain also for this function is equal to R, which is of course also written as -infinity to +infinity. Now I must admit, these two first exercises were quite straightforward. However, they serve as an introduction. So let's go to the third exercise where we'll have to do some more thinking. In this exercise, we will look at the function f of x is equal to 1 divided by the cosine of x. And this is our first encounter with a rational function, meaning that we have an enumerator and a denominator, and more specifically, an x appearing in the denominator, which is always a sign that you should be careful when determining the domain of this function. And in particular, for rational functions, meaning when we have x's in the denominator, we always have to be on the watch for 1 divided by 0, because 1 divided by 0, of course we know, is ill-defined. And for this specific x, the function returns a 1 divided by 0, then we know that we have found a specific x for which this function cannot return a valid value. And this is exactly the reasoning that you should do when you come across functions with x in the denominator. And we see here in this case that we clearly have an x in the denominator, namely inside this function cosine of x. And thus the question that you should ask yourself in these cases is, when is the denominator 0? Because if the denominator is 0, we get an invalid output. And for this specific function, this question boils down to for which x is the cosine of x 0? Because if we found this x, then we know that this x as an input to our function leads to 1 divided by 0 and thus an invalid output. And therefore this x would not be part of the domain of this function. So we have to solve this equation right here. And knowing the functional behavior of the cosine of x, we know that the cosine of x is 0 if x is equal to pi over 2, 3 pi over 2, and so on, always adding pi. But also in the negative direction, if x is minus pi over 2, minus 3 pi over 2, and so on. So for all of these values, the cosine of x is 0. And therefore, we know that the domain of this function will be any number except for all of these values. So we need to write down the set that includes all of these values. And we can do so as follows. So x is an element of the following set: pi divided by 2 plus minus any whole number multiplied by pi. And any whole number we can indicate by saying that n has to be an element of the natural numbers. For example, if n is equal to 0, then we simply get pi over 2. If n is equal to 1, we get minus pi over 2 with the minus sign and plus 3 pi over 2 with the plus sign, and so on, such that we have all of these values right here. And now that we've written down the set of numbers for which the cosine of x is equal to 0, we know the set of numbers for which 1 over the cosine of x cannot return a valid number, since we simply get 1 over 0. Therefore, we know that the domain of this function will be all of the numbers except for this set that we found right here. So the set of pi over 2 plus minus a natural number times pi, with this natural number being, well, a natural number. And this will be the solution for this exercise. These are all the numbers, so most of R, such that this function returns a valid number. The main thing to take away from this exercise is that whenever you have a function where there is an x in the denominator, and this x itself could be in a function, such as here in the cosine of x, then you need to ask yourself the question, when is the denominator 0? Because when the denominator is 0 and the enumerator is just a number, this means that the function does not return a valid number. In the next and fourth exercise, we are going to be looking at the function f of x is equal to the square root of x minus 1. And here, since we do not see any denominator, you might think that we're in the clear and that the domain is simply all of the real numbers. However, we need to be wary because we know something more about taking the square root of a real number. In particular, we know that taking the square root of a negative number does not return a real number. It is only when we consider the complex numbers that this actually returns a valid number. Namely, the square root of minus 1 is in that case simply the complex number I. But that I cover in detail in my series on complex numbers, which you can find in the description below. Going back to our initial problem, we need of course to look for the domain of this function, meaning we need to find the subset of all x's such that this function returns a valid number. Now in this particular case, returning a valid number means that the thing inside of the square root needs to be larger than 0. So it needs to be positive, because we can only take a square root of a positive number. With this reasoning, we know that x minus 1 needs to be larger than 0. And of course, we can bring this minus 1 to the other side of the inequality sign, and thereby leaving the inequality sign as is, in order to get that x needs to be larger than 1. And if x is larger than 1, that means that x minus 1 will be larger than 0. And if x minus 1 is larger than 0, we know that the square root of this number, x minus 1, will be indeed a real number. And just like that, we found our domain. Simply any x that is larger than 1. Because for these x's, the square root will return a real number. So we find that the domain is equal to the set of all x's for which x is larger than 1. And this is our domain. However, what about x is equal to 1 exactly? Because at this point, x is equal to 1 is not in our domain. So let's simply fill x is equal to 1 in our function. That would mean that we get the f of 1. Filling this in our square root, we get the square root of 1 minus 1, which is of course the square root of 0, and the square root of 0 is indeed 0, so a valid output. This of course means that x is equal to 1 is exactly at the boundary, but it is still included in our domain. Therefore, we adapt our domain such that x is larger or equal to 1. And at this point, this is indeed the right domain for this specific function. And the thing to take away from this exercise is that whenever you have a square root, just remind yourself that the thing inside of the square root should be equal or larger than 0. So let's now go to the fifth exercise, where we're going to look at the function f of x is equal to the tangent of x. And there's two ways to approach this. And the first way, which is the less generic way to approach it, but I mention it either way, is that you have a clear idea of how the tangent of x looks like on an xy graph. So on the y-axis, we have the tangent of x, and on the x-axis we have x. And now the graph of the tangent of x looks like this. It goes through 0, and it has these two asymptotic lines. And then simply it repeats itself to the positive side of x and to the negative side of x, and it repeats all the way up to plus or minus infinity. And now you might recall from your goniometric classes that the tangent of x has these asymptotic lines in a periodic interval at all of these points. And if you have a really good memory, then you remember that they occur at multiples of pi over 2, both in the positive and in the negative direction. And from this, you know that the domain of the tangent of x is simply the complete x-axis, so all of r, the real numbers, without the following set of numbers. So all of the pi over 2's, and from this you could directly see that the domain of the tangent of x is simply all of the real numbers without all of these multiples of pi over 2, with n being a natural number. However, this method does not give us a generic approach to finding the domain. For example, for many functions, you do not know by heart the graph of the function. Therefore, we will look at a second and more generic way of finding the domain of any function. And to do this, we only need to remind ourselves of one thing, namely that the tangent of x is equal to the sine of x divided by the cosine of x. And at this point, our internal alarm should go off, because we see that we have an x in the denominator of this function, namely the x inside this cosine of x. And we know that this could lead to a 1 divided by 0, which of course would not return a valid result, and so all of the x's for which the denominator returns a 0 are points that are certainly not in our domain. And therefore, we again ask ourselves the question, when is the denominator 0? Or in this case, when is the cosine of x 0? But this is exactly what we've done in the third exercise, where we were looking at the function 1 over the cosine of x. So we know that the cosine of x is equal to 0, for x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, and so on and so on. And because we know that for these x's our denominator is 0, and that a 0 in the denominator while the enumerator is not 0, gives us an invalid output. Or in other words, these x's are not part of the domain. And therefore we conclude that our domain is simply all of the real numbers without the following x's, namely pi over 2 plus or minus n, for which n is a natural number. And now at this point, of course, we see that the result that we've gotten from looking at this cosine in the denominator gives us the same result as the graphical interpretation, where we had to remember how this graph exactly looked and all of these numbers, at which point there was an asymptote. And now that we've got some experience under our belt, let's go to the sixth and final exercise in finding the domain. In this exercise, we're looking at f of x is equal to the sine of x divided by x. And this is quite of a complicated or hard example because it's quite of a trick question and you need some more advanced mathematics to solve it. However, we'll do it either way and step by step, and you might be able to follow along the way. To find the domain, the first thing that you should notice is of course this x in the denominator. And this in a sense is good news because you know that whenever there is an x in the denominator, the question you should ask yourself is, when is the denominator 0? Because if the denominator is 0, then we divide by 0 and this is invalid. And thus these x's are not part of the domain. And in this specific case, this is quite straightforward. Namely, x is 0 when, well, x is 0. So the denominator is only 0 when x is equal to 0. So we could conclude that the domain is simply all of the real numbers without x is equal to 0. Problem solved, right? Well, not exactly. Because at this point, we need to address a subtlety when looking at when the denominator is 0. In all of the previous exercises, I said that when the denominator is 0 and the enumerator is not 0, then indeed you have a divergence or you have an invalid output. However, in this case, let's fill in x is equal to 0. So f of 0 is equal to the sine of 0 divided by 0. Now we know that the sine of 0 is also 0. So in this case, we get 0 divided by 0. And therefore, you cannot directly conclude that x is equal to 0 will lead to a plus or minus infinity and therefore an invalid result. We'll have to do some more work to get rid of this 0 divided by 0. And to investigate this function around the point x is equal to 0, we use what is called a limit of x is going to 0 of the function the sine of x divided by x. And what this basically means is that we don't plug in x is equal to 0, but we're just letting x approach 0 and then see what the behavior of this function is. Now again, simply filling this in would give us 0 divided by 0. But at this point, we need to remind ourselves that there is actually a trick that we can do to solve this limit, namely L'Hopital's rule. And if you're not familiar with L'Hopital's rule, I have a video that is completely dedicated to solving exercises on L'Hopital's rule. What L'Hopital's rule says is that we have to derive the enumerator and the denominator of this function and then take this limit again. So this means that we have the limit of x going to 0 of the derivative of the sine of x, which is of course simply the cosine of x, and the derivative of x is simply 1. And looking at this function, we see that we can simply plug in x is equal to 0, because in the denominator x has disappeared, and in the numerator we simply have the cosine of x. So filling this in, we simply get 1 divided by 1, which is of course 1. But what does this now actually mean? Well, this means that the function f of x is equal to the sine of x divided by x. If we now let x go to 0, instead of plugging it simply in and thereby getting 0 divided by 0, we know that at x is equal to 0, this function simply becomes 1 and not plus or minus infinity. And this is important when determining the domain of this function, because we saw that x is equal to 0 is the only point that might lead to a domain that is different from R. However, using some smart tricks, namely taking the limit and using L'Hopital's rule, we found that x is equal to 0 actually leads to a function value of 1. And thereby, after all this work, we conclude that the domain of this function is simply R, all of the real numbers that you can imagine. And this includes x is equal to 0, which was not clear at all from the start. And this brings us to the end of this video, and I hope that you're now much more familiar with the concept of the domain of a function and that you're now more confident in solving such exercises. As always, if you have any questions, leave a comment in the comment section down below. If you liked the video, give it a thumbs up, and I will see you in the next one. Bye.